Welcome to our lesson on solving trig equations, today using identities and by graphing. So we've already looked at how factoring could be useful in solving and how we can use inverse operations to get one trig function in an equation all by itself, which looks pretty typical to what we see in an algebra class. So we're going to add to that toolbox today. Just remember though, when we're solving, we're looking for all of our solutions, and those solutions are angles. So by default, we're looking for all angles in radians, and unless we're directed to do something else like find all solutions in degrees or look only over the interval from 0 to 2 pi or 0 to 360 degrees. So if we're specified to do something else, we're looking for all of our solutions which are angles, and we're looking for those angles in radians. And then also remember that it's preferred to give exact solutions. So if we can get our solutions off the unit circle and put them in exact form, that's going to be preferred, but sometimes it isn't possible. So if it's not possible, then we'll use a calculator to approximate. And we could also use the calculator to verify the exact solutions. Okay, so today we're going to look at solving using identities first. And this is going to be an approach that we may have to use when more than one trig function in your equation exists, which we actually saw that in the previous topic, but factoring won't be possible. So if you have more than one trig function in your equation and factoring isn't an option, then you're going to try to use identities to make some substitutions. The goal would be to make substitutions using identities to get just one trig function in the equation. All right, and then it might be necessary in these types of cases to square both sides of the equation. Remember, as long as we do the same thing to both sides of an equation, it's technically a legal move, but we really have to be careful with this one, because when we square both sides, we are increasing the degree of our equation, which increases the number of possible solutions. And so the solutions that we introduce may be extraneous. So this option might be necessary for us to make substitution, but it also is something that could introduce extraneous solutions. And if you remember from a college algebra class, extraneous solutions are solutions that you get by, using correct algebra and solving techniques, but when you plug that solution back in, it doesn't produce a true statement. It's not a valid solution. Okay, and I'll show you when one of those comes up. Okay, so let's try it out. For example, number 1, we're trying to solve -2 times cosine squared theta plus 1 equal to sine of theta. So again, we saw in our previous topic 2 different trig functions in one equation, but we saw the terms with something in common, and that's not happening here. So again, our goal is to be using an identity to try to make a substitution in order to get this in terms of just one trig function. So if I could get this just in terms of cosine or just in terms of sine, then I would be in better shape than I am now. And hopefully it's seeming familiar to you, but cosine squared, that's in one of our Pythagorean identities that is used quite a bit. That cosine squared plus sine squared is equal to 1. That means I could replace cosine squared with 1 minus that sine squared if I moved that over. So that's what I'm going to do here. I'm going to take this, leave the -2, take the cosine squared, and replace it with 1 minus sine squared. And then I still have the plus 1 equal to my sine of theta. And now I have one equation that only has one trig function in it. Now, the two terms that contain the sine function have a varying degree, so now I'm going to try to use my factoring approach. So let me distribute this. I've got a -2 here, and then a +2 in front of my sine squared theta. Then I still have this plus 1. I'm going to subtract the sine of theta over. If I'm going to try to factor, I want a 0 on one side. Now let me put this in order and combine my like terms. So 2 sine squared theta, and then minus the sine of theta. And then if I combine the -2 and the +1, then I have a -1, but now it's all in order equal to 0. And again, I can try to factor. So if you need to rewrite this, technically, get a good color here, this would be like factoring 2a squared, it's supposed to be a square, minus 1a minus 1, where we would be looking for factors of -2 to make -1, like -2 and 1, and dividing by 2, and then reducing, we see that this would factor into 1a minus 1 and 2a plus 1. Now, technically, I did this. You're welcome. I replaced the sine of theta with a. So now in my factorization, I want to replace a in both of these with the sine of theta. So my correct factored form for my trig equation is going to be the sine of theta minus 1, and then twice the sine of theta plus 1 equal to 0. And remember, if you can skip this, if you can do the factoring without having to rewrite it, that's awesome. If not, totally fine to take that extra step. Alright, so from here, if I can make just one of my factors equal 0, I can make my whole equation equal 0. So I'm going to look for what's going to make the sine of theta minus 1 equal 0, and also what's going to make twice the sine of theta plus 1 equal 0. So over here, oops, my eraser turned on. What's going to make the sine of theta equal 1? Go to my unit circle, which I think I have one handy right here. Yep, where's my sine going to be equal to 1? And actually, let me go back. I am solving this looking for all solutions, okay, not just over a specific interval. So where's my sine going to be equal to 1? Remember, my sine is my y value, so I have a y value of 1 here, and that's going to be the only place. So that's going to be at pi over 2, and every time I lap around a full 2 pi, I'm going to land there again. And so pi over 2 plus 2 pi n is going to be one set of my solutions. So here we're going to say, my pen is on, theta is going to equal pi over 2 plus 2 pi n times. And then over here, we're going to want to subtract over the 1 and then divide over the 2. So we're looking for where the sine of our angle is going to be equal to a negative 1/2. So again, back to our unit circle. Where do we have a sine value of negative 1/2? So sine, again, being our y value, negative 1/2 right there at 11 pi over 6, and negative 1/2 here at 7 pi over 6. So we're going to say it's 7 pi over 6 plus 2 pi n and 11 pi over 6 plus 2 pi n, because every time I lap around the unit circle, I'm going to land at those locations again. So back to this. So theta is going to equal, I already forgot, 7 pi over 6 and 11 pi over 6. 7 pi over 6 plus 2 pi n and 11 pi over 6 plus 2 pi n. And we did it. So we have these solutions as well as these solutions. So if I just said to solve over the interval from 0 to 2 pi, then you would just keep these three angles. But because I can keep looping around to get to those locations, those would be the infinite solutions. Alright, get rid of all those highlighters now. Okay, we did it. First one, done. So actually, more the work comes from the factoring and in the isolation that we've talked about already. It was just that one step in the beginning to get the substitution in there, get the one trig function in, so that we can apply those other approaches. Alright, let's try this again. So number 2, it says to solve on the interval from 0 to 2 pi. If I'm looking at this equation that contains two trig functions, again, factoring not an option because the terms have nothing in common. And if I'm trying to think about an identity to use, a substitution to use, I can't really swap sine or cosine out. Like, I can't swap sine out with anything that's going to make it a cosine, and I can't swap cosine out with anything that's going to make it a sine. So I can't get rid of one thing and get this equation in terms of just one trig function. So this is a case like what I talked about or mentioned in this second bullet, where we want to square both sides. Because if I have a sine squared or a cosine squared, I can use that Pythagorean identity to make a substitution. So I'm going to square both sides of my equation, square here and square here. This means I have to multiply a sine of x minus 1 by itself. So we have to be careful with that work. On the other side, cosine times cosine is just cosine squared, so that's not a big deal. So over here, sine times sine makes a sine squared. Sine times negative 1 makes a negative sine of x. Again, here, a negative 1 in front of my sine of x. And then negative 1 times 1 makes 1. Now, on the other side of the equation, I have this cosine squared. But I can get rid of that using the same Pythagorean identity we used in the last one. So cosine squared, again, equal to 1 minus that sine squared. If I swap that out, then I have one equation that only has sine in it. So I'm going to swap out the cosine squared with 1, that's my highlighter, 1 minus the sine squared of x. So now that I have one trig function, again, but with varying degrees, I'm going to try to get this thing in a factorable form. So everything on one side equal to 0. So I'm going to subtract these terms over, subtract the 1 from both sides, which actually is going to it's going to cancel it on both sides, so that's nice. I'm also going to add over the sine squared x to its like term, so that's going to be gone again from this side. So what I'm left with is a sine squared plus another sine squared, which makes 2 sine squared of x. And then I also have like terms here. I can combine negative 1 sine and negative 1 sine to make negative 2 in front of my sine of x. And then the 1's canceled, so nothing left, just my equal and my 0 that I was trying to get so that I could put this in factored form. So now that I factor, the two terms left in my equation, they have a 2 in common, and they have a sine of x in common. So I'm going to factor out 2 times the sine of x, which means I'm dividing. So when I divide my first term by 2 sine of x, I'm going to have a sine of x left. Right? The 2 divided out makes a 1, and dividing one of the sine x's out leaves me 1. It's a factor of sine of x. And then here, dividing negative 2 sine of x by itself leaves me a minus 1. And that's a gigantic eraser. How about that one? Okay, so now that it's factored, and again, equal to 0, making each of the factors equal 0 is going to give me a solution. So what's going to make 2 times the sine of x equal 0? And what's going to make the sine of x minus 1 equal 0? So over here, if I divide the 2 over, I'm still going to have 0 divided by 2, which is 0. So I'm looking for where my sine is equal to 0. So we go back to my unit circle. Where do I have a sine or a y value of 0? So y value of 0 happens here. It also happens here. And let me go back to where am I looking? All solutions just 0 to 2 pi. Okay, so from 0 to 2 pi, I can say 0, I can say pi. I don't want to say full circle 360 or 2 pi because that's not included. It was in parentheses. So we're going to say 0 and pi for now for that one piece of my equation. So we're going to say here x is equal to 0 and x is equal to pi. And then over here, I'm going to add 1 to say, or figure out now where is my sine of x going to be equal to 1. So back to my unit circle. Where do I have a sine value of 1? Only happens right here at pi over 2. So then here we're going to say x is going to be equal to pi over 2. Now, my original equation, if I was looking at this, like I don't know instinctively or intuitively how many solutions you would be thinking to look for over the interval from 0 to 2 pi, but I might guess that because I have a sine and a cosine, that 2 solutions would work, although it's going to also be hard to tell here. The thing is, because we squared both sides, we could have introduced a solution that's not going to be valid. So I have to check all of these solutions and make sure they work, which is good practice, especially if you're taking a quiz or a test. Not necessarily something I want to do every time, but let's check to make sure that all 3 of these solutions are valid. So if they're valid, that means when I plug them into my original equation, I should get a true statement. So the original equation says the sine of the angle minus 1 should equal the cosine of the angle. So if I go to plug this one in, right, the sine of my angle 0 minus 1 should equal the cosine of my angle 0. So sine of 0, if I go to 0, my sine is 0. So sine of 0 is going to be 0. And then I have to subtract 1 from that. The cosine of 0, again, cosine of 0, that's right here, that's 1. I'll look back and forth, sorry, it's going to be 1. And 0 minus 1 is negative 1, and negative 1 does not equal positive 1. So since that is a false statement, this is going to be an extraneous solution. It's not a valid solution. We didn't do anything wrong in the solving process. It's just because we squared both sides, we introduced the possibility of this happening. So that's an extraneous solution, which means we're not going to box that in as a valid solution to this equation. Now let's check the others. Let's check pi. So this should be the sine of pi minus 1 equal to the cosine of pi. So at pi, that's 180 degrees. I need the sine and the cosine. So at pi, sine is 0, cosine is negative 1. So at pi, sine was 0, and cosine was -1. This time we get -1 equal to -1. That's going to be a valid solution, so we're going to box that one in, keep that one. And then I just have one more to check. Let's do, how about grade this guy over here? So one more to check. Again, the sine of pi over 2 minus 1 should equal the cosine of pi over 2. So pi over 2, that's 90 degrees. At 90 degrees, our sine is going to be 1, cosine is going to be 0. So sine is going to be 1, and then cosine is going to be 0. And so we get 0 equals 0. Again, a true statement, which means this is going to be a valid solution. So 2 of those work, 1 does not. Right? This being false means this is not a valid solution. This being true means it is. And then again, this being true means that's valid. So of the 3, we got 2 that worked and then 1 that did not. And then, I mean, I sort of had the feeling that that was going to happen, but there's just really no way to tell sometimes. And so if you have squared both sides of your equation to solve, you're going to have to check your answers. All right, so that one extraneous not going to count. Okay, and luckily we only had to go from 0 to 2 pi, so we don't have to lap around and talk about all the infinites. All right, let's look at number 3. So number 3, I have multiple trig functions in this equation, but they're not the same, no common factors to factor right up front. So I need to make a substitution. And this is another Pythagorean identity that we can use. Let's see. We have cotangent squared 1 plus, 1 plus cotangent squared theta equal to cosecant squared theta, or x, or I'm not sure how we wrote that on your list of identities on your reference sheet, but that's an alternative form of our Pythagorean, like I think the third one that we put in our boxes. So I can replace cotangent squared with cosecant squared minus 1, and if I do that, then I will only have cosecant in my equation. So I'm going to, this was connected to this problem, not to be confused with all the work I was doing above, replace cotangent squared with cosecant squared minus 1. And then I have this minus 4 cosecant of theta here, and I'm going to go ahead and add the 5 over to make this thing equal to 0. Because I have the varying degrees of those trig functions, I know I'm going to be trying to factor this. So I have cosecant squared theta, I have a -4 cosecant of theta, and then if I combine my -1 and my +5, I'm looking at a +4 now equal to 0. And if you can factor without rewriting this, awesome. If not, you're looking at something like a squared minus 4a plus 4, and looking for factors of +4 that make -4, like -2 and -2. So this quadratic would factor into an a minus 2 twice, a minus 2, a minus 2. Now I replaced cosecant with a, so now I'm going to replace these a's with cosecant. So my trig function in factored form is going to be the cosecant of theta minus 2 twice. So if you didn't want to write it twice, I mean, you can write this as the quantity squared. That would be a little bit more concise, although it's not really going to matter. From this point, we know we're trying to make each of the factors equal 0, so what's going to make cosecant theta minus 2 equal 0 is going to be enough. If you had written this as a square, then you could take the square root of both sides, with the square root of 0 being 0 is going to leave you just one of those factors to solve anyway. So however you want to write that and continue would be totally fine. So where's our cosecant of theta minus 2 going to equal 0 means where's our cosecant of theta going to equal 2? And sometimes hard to hold too much in my head. Cosecant, remember, is the reciprocal of sine. So if the cosecant of our angle is equal to 2, that means the sine of our angle is equal to 1 over 2. So we can go to our unit circle for that. Where is our sine? A positive 1/2. So we have a positive 1/2 for sine at pi over 6, and we have a positive 1/2 for sine at 5 pi over 6. And we are looking for all solutions, or yep, all solutions, just says to solve. So again, we're going to say pi over 6 plus 2 pi n and 5 pi over 6 plus 2 pi n to get all those infinite solutions in there. So theta is going to equal, running out of room, pi over 6 plus 2 pi n times, and theta is going to equal 5 pi over 6 plus 2 pi n times, and those would be our infinite solutions in radians. Okay, we did it. Now I think this would be a good place for you to pause the video and try this one out. Trying to solve on the interval from 0 to 360, so we don't have to lap around the unit circle, and we're looking at angles in degrees this time. But if you want to solve this, you're going to have to make a substitution, and you've got a couple of different ways to go. So if you're feeling pretty confident here, then pause the video and try this out. Otherwise, just continue with me here. So we can either get this in terms of cosine or get this in terms of sine using that Pythagorean identity I used on number 1 and 2. I think I'm going to swap out cosine again, so I don't have to worry about the negative. Cosine squared is 1 minus sine squared, so I'm going to replace cosine squared with 1 minus sine squared. And then I still have this minus sine squared from the original equation equal to 0. And if I combine those like terms, combine my negative sine squared and negative sine squared, then I have 1 minus 2 of those sine squareds equal to 0. And I can factor this, but I don't need to because now I only have one term in my equation with a trig function in it, so I can just get that sign by itself using inverse operations. So I'm going to subtract the 1 over. So negative 2 sine squared is equal to negative 1. I'm going to then divide the negative 2 over. So sine squared is going to be equal to negative 1 divided by negative 2 makes a positive 1/2. And then I'm going to take the square root of both sides. So that's going to give me the sine of x equal to a positive or negative. The square root of 1 is 1. The square root of 2 I can't take, but I can rationalize this so that it looks a little more familiar. So we're going to be looking at plus or minus radical 2 over 2. So our angles from 0 to 360 in degrees, where are we looking? Where do we have a sign that is positive or negative radical 2 over 2? Hopefully you're kind of knowing these without having to go to your unit circle, but our sign being positive or negative radical 2 is going to happen at all of our 45-degree reference angles. So we're at 45, at 135, at 225, and at 315. Now if I said to find all solutions over the interval, or all solutions, like not all solutions, let's say in degrees, then I could just say 45 degrees plus every 90 degrees n times, or because I'm only going, or if I was in radians, I would say pi over 4 radians plus every pi over 2 n times, because every 90 degrees I am landing in one of those, on one of those angles. Now, since I only asked for 0 to 360, I'm going to just specifically list those angles out. So let's say 45 degrees, 135 degrees, 225 degrees, and then lastly 315 degrees, and those would be all of our angles, again from 0 to 360. Okay, hopefully if you paused, you did that correctly. If you did, good job. We survived method number 3 of solving. So now let's look at the fourth option, solving by graphing, which I really like this option. Sometimes it's a necessary option, sometimes it's just a great way for you to verify the work that you're doing algebraically. If you were restricted to solving without a graphing calculator, then obviously this would not be an option. But if you have a graphing calculator, this is a great option. And actually, graphing can be used to solve any equation. I don't know if you realize this, but yeah, this is true. Okay, we can use graphing to solve any equation, and I can probably show you. So don't write this down, but just so you understand, like a simple equation, let's just say 2x plus 1 equal to 5. Like I know the solution here is going to be 2. 2 times 2 would be 4 plus 1 is going to make 5. I don't need technology for that, but just so you can see, if you make one side of your equation a function, let's call it y1 here, make the other side of the equation a separate function. If you graph both sides as separate functions, then you're looking at a system of equations. Now, if you remember from college algebra, when you graph a system, the points of intersection for the system happen to be the solution for the system. So that would be true here if we just make our equation a system. So if I was to type in 2x plus 1 as one equation, why my calculator keeps doing this weird thing with the keyboard? I don't know. Let's call the first equation y equals 2x plus 1. So I'm going to make one function out of one side of the equation, make another function out of the other side, so y equals 5. And the point of intersection there at 2, 5 shows me the solution. Now technically, it gives me an intersection, right? But all I would be solving here for is x, and I know again the solution was 2. That occurs in the x value of that intersection. So what we're going to do is we're going to make a system out of one equation. If we just input each side of the equation as a separate function, look for the intersections, the x values in those intersections are going to be our solutions. Okay? So hopefully that made sense. If you remember your work from college algebra. So much college algebra coming into play here, right? So we can actually use this to solve any equation, including the ones we'll look at today. So what we're going to do if we want to solve one equation using graphing is we're going to input each side of that one equation as a separate function to graph. And then the x values of the intersections of the two graphs are going to be the solutions. Again, that's the x values in those intersections. Remember, when you're solving for x. Okay? And this option might be necessary if algebraic options weren't possible, and we're going to see one of those. Otherwise, it's just really a nice option if you have a graphing utility. And you can definitely use this to verify work that you would be doing on any of the equations that we've solved so far. Okay? So the first one here, number 5, I graphed it, although I think it would be good practice for us to go through the solving by hand. If we were going to solve this by hand over the interval from 0 to 2 pi, we would have to square both sides to make some sort of replacement. So what we saw like in number 2, okay? If I squared both sides of this equation, then I'm looking at sine squared of x equal to cosine squared, and then I can replace either sine or cosine. I've done a lot with sine, so I'm going to get rid of that one this time. I know that using that same Pythagorean identity, right? Cosine squared plus sine squared being equal to 1. I could say sine squared is 1 minus cosine squared. So 1 minus cosine squared x equal to cosine squared x. And then these are like terms. So I'm going to add this cosine over to the other side. So I have 1 equal to 2 of those cosine squareds. And then I'm going to divide the 2 over. So I have 1/2 equal to cosine squared of x. And then I'm going to take the square root of both sides. So square root. And now I can see that the cosine of x is going to equal plus or minus. Again, square root of 1 is 1. Square root of 2 I can't take. But if I rationalize that, then I'm looking for, I'm just going to write this my normal way, the cosine of x being equal to plus or minus radical 2 over 2. Okay? So actually what we just did a second ago, but well, let's go back to the unit circle. So we want to know, where's our cosine equal to a positive or negative radical 2? Same places we were just looking. Those that are all our 45-degree reference angles. And here we're just solving over the interval from 0 to 2 pi. So I would say positive or negative, but remember, I squared both sides. Let me write these out. Change back to blue, sorry. Okay, so I said all the 45s. So that was pi over 4, and 3 pi over 4, and 5 pi over 4, and 7 pi over 4, right? But because I squared both sides, I introduced these extraneous solutions, or the possibility of extraneous solutions, so I would have to check these. So all I'm looking for technically is if I input my angle, the sine and the cosine have to be the same. So at pi over 4, the sine and cosine the same, yes, so that's going to be a valid answer. At pi over 2, they're not the same because negative pi over 2 and positive pi over 2 have different signs, so that's an extraneous solution. Here they're the same, so that's good. And here they're opposite signs, so that's extraneous. So back here, we got extraneous solutions in quadrant 2 when we had different signs, and quadrant 4 when we had different signs. So since those are extraneous, the only valid solutions we should see are at pi over 4 and at 5 pi over 4 over the interval from 0 to 2 pi. So by hand, the only way to do this, well, one of the ways to do this is to create the possibility of the extraneous solutions, have to verify our work, and we get those two answers. Now, if you're going to solve graphically, it's so much simpler, okay? I put the graph here for you, but I'm going to do this in Desmos as well. What you would do if you wanted to solve this graphically is you would make each side its own function. So I'm going to call one side a function, y equals the sine of x, and call the other side a function, right, y equals the cosine of x, and graph those two things. So if I graph y equals, darn calculator, the sine of x, maybe if I put an equal sign in there, that would be good. And then y equals the cosine of x. And something's wrong with my picture. There we go. It's because I was in, and you'll see it clearly, right? I was in degrees, so that did not look right. So radians. So here we go. The two solutions we said would be pi over 4 and 5 pi over 4. If you graph these two functions, again, each side of the equation as its own function, the intersections of the two functions, where are the points where the two graphs cross? Here's one point, and the x value, notice in that point, is one of the solutions we got here at pi over 4. So this point right here, where those two graphs cross, is a solution. So it says pi over 4, and then 0.707, but that part of it doesn't really matter, okay? The other point where these cross is down here. That's the other solution we got. So that intersection right there at 5 pi over 4 and negative 0.707 is our other solution. So over the interval from 0 to 2 pi, the only two places they cross are the only two valid solutions we get when we're solving by hand. And remember, all we want is the x value in that intersection. So 5 pi over 4 and pi over 4. The y value that's there is the output. So the cosine and the sine at pi over 4 are both radical 2 over 2, which was approximately 0.707. And at 5 pi over 4, both the sine and the cosine are negative radical 2 over 2, which is about negative 0.707. So we can do the work by hand, and it's good to be able to do that, but you see how much faster and easier the graphing option is. So if we look at number 6, again, good practice for us to do some solving by hand, but I can already see I'm going to have a solution here, and this one says find all the solutions in degrees. So if I'm looking for solutions, I'd be looking for intersections. My calculator is going to do this really nicely for me here, but I can see a couple of them nicely right here, right smack in the middle of 90 and 180. So think about that's your, we're in quadrant 2 there. What's right in the middle of quadrant 2 is our 135 degrees. I can already see that's going to be a solution. And then the same here. I have a solution right in the middle of 270 and 360, which is our 315 degrees. But then I have a solution here. My graphs are crossing there, and I have a solution here, and I can't see exactly where those are, right? So these are going to be some approximate solutions, and I have a couple of exact solutions. So now, granted, my calculator, when I put this in Desmos, it's going to show me those exact values and those approximate values, but because we need the practice, let's do this by hand and see why those 4 intersections are happening. So if I was solving this by hand, I only have cotangent in there, so I don't have to worry about making any substitutions. Cotangent squared x. I'm just going to subtract over the cotangent, subtract over the 3 so that I can factor this. And I'm going to do this without rewriting it. Hopefully you can follow me here. I'm looking for factors in negative 6 to make negative 1, like negative 3 and 2. Dividing by 2, and then reducing. Normally it would be 2x minus 3. This is going to be 2 cotangent of x minus 3. So this is 2 cotangent of x minus 3. And then over here, normally 1x plus 1. This is going to be 1 cotangent of x plus 1. And so I want to know, where is the cotangent of x minus 3 going to equal 0? And where is the cotangent of x plus 1 going to equal 0? Oh, sorry, I forgot my 2 over here. So on this first one, I would have to add over the 3, and then divide over the 2. So I'd be looking for the cotangent of x to be equal to 3 halves. Well, cotangent, remember we get this by dividing a cosine by sine. The only options are to get a radical 3 over 1, a 1 over radical 3, a 1, or a 0. 3 halves is not going to happen anywhere on our unit circle. So the only way to get the answers here would be to use our inverse cotangent. And so putting that into the calculator would give us the approximation that we're going to see happening over there. Now, let's go to the let me actually finish this one off, because this one's easy. Cotangent of x equal to -1. So at what angles can we divide our cosine by our sine and get a -1? So that's going to have to happen in quadrant 2 where we have a positive and negative, and in quadrant 4 where we have a positive and negative, and that's going to be at our 45s there. So we're in degrees, right? That's going to be at 135 degrees and at 315 degrees. And actually, that's exactly what I showed you on the picture there, right? Right smack in the middle of 90 and 180 and 270 and 360 are those 45-degree reference angles. So I got 2 of those by hand pretty easily. It's the other 2 that are a little strange that are happening over here. So let's go to the calculator. If I was going to use my calculator to graph, I would put one side in as one equation and one side, or one function, one side in as another. So I'm going to put y equals the, let's see, 2 times the cotangent of, cotangent squared of x, and then cotangent y equals, come on, you can do it, cotangent of x, and then plus 3. Okay, so there's the picture that I have already put onto the graph for you. And right now my calculator is in radians. In this problem I'm trying to work in degrees. So let me change this to degrees. And that means I gotta change my axes here. I want it to go from 0 to 360 just to get a picture like the one I put on your paper here. Let's make that go by 90s, and then, like, I don't know, -5 to 5. Let's try that. Okay, so this looks good. Here's our picture. 0 to 360, I can see at 135, I got that solution. And at 315, I got that solution. Now this solution, about 33 degrees and then 213 degrees, those 2 decimals we would get by finding the inverse cotangent of 3 halves. And there it is, 33 degrees. Now be really careful, because normally your calculator's in radian mode. If you are in radian mode, then you're getting about 0.58 radians, but we don't want that. Remember, we want to be in degrees. And so in degrees, this is going to be approximately, we said 33, let's just say 33.7 degrees. And then cotangent, again, negative is, or actually this one is a positive cotangent. Cotangent's going to be positive, and oh my gosh, I got too much on my screen. Over here we had a negative cotangent, so we took the values that were in quadrants 2 and 4. Here, cotangent is going to be positive in quadrants 1 and 3, so that's why we see the solution up here at 33.7-ish, and then over here is in quadrant 3, and that was 213.7-ish, so 213.7, and then the other part of the point was 4.5, and that was 4.5, and over here we were at 135 and 2, and then over here we were at 130, just kidding, 315 and 2. So all 4 of those, super nice, easy. We can get those from the graph, but just so you can see by hand, that's the work that would be involved there too. So 33.7 and then 213.7. Now, those 4 solutions are only the solutions from 0 to 2 pi. This one technically says to find all of the solutions in degrees. So how could we describe all of these solutions? Well, the solutions are 180 degrees apart. If I added 33, if I added 180 degrees to that, 3, that's 1 and carry the 1, that's 213. If I have 135 degrees and I add 180 to that, I'm going to end up with 315. So I actually don't have to state all of those solutions. I just need to state the first one, and then I can add 180 degrees to each of those. So to concisely state these solutions, we're going to say x is going to be equal to 135 degrees plus 180 degrees n times, and then x is also going to be equal to about 33.7 degrees plus 180 degrees n times. So there they are, our infinite set of solutions in degrees. Much easier to get those just by going to the graph, but again, practicing by hand, good practice. All right, so let's look at number 7. Even if I wanted to do number 7 by hand, it's not going to be an option for me. We're not going to be able to solve this, well, in our current state of mathematical skill, be able to solve when we have sine and cosine and a cubic and quadratic function in there. So what we're going to do is strictly go to our graph. So I'm going to call this y equals x squared plus the sine of x, and I'm going to call this side y equals x cubed plus the cosine of x, and I'm going to graph those two and find where the graphs intersect. So let me just delete all, goes back to a normal window here. Oh, why did I? Okay, I'm in radians. I need to go back to radians. So, actually, nope. And my calculator's already. I'm thinking here. My calculator's already in radians. I should be good. So let me just type this in. Y is going to equal. One side of my equation is y, x squared plus the sine of x, and the other side of my equation, y equals x cubed plus the cosine of x. Okay, so from 0 to 2 pi, which means, yeah, I need to fix my axis. Go from 0 to 2 pi. Let's go by, doesn't really matter, but I'm going to say pi over 2. And then over here, like negative, I might have to mess with this, but just so I can start somewhere. Okay, so 0 to 2 pi looks like we're only going to be crossing, this you're just going to get farther apart. From 0 to 2 pi, we're going to be crossing twice. These are going to be the two intersections in there, and let me write those down. I have two intersections in the window from 0 to 2 pi. One is at 0.681 and 1.092, and the other at 1.416 and 2.993. Those two intersections are going to show me my solutions. Remember, I'm only solving for x, so this is sort of arbitrary information. Well, I mean, it's not arbitrary. It's meaningful. It means that at an x value of 0.681, like if I plug that x value in, I get both of those sides of the equation to be the same, and that would be what the output would be. But it doesn't matter in terms of our solutions. We're just trying to solve for x in this picture, so my solutions are here. So if I said solve this, you're going to say x is going to be equal to approximately 0.681, and x is approximately 1.416, and we did it, okay? And really the same process could have been used for every single equation that we've done, or that we've done here, but that work by hand is using skills we need, okay? So hopefully that makes sense, and hopefully now you have a nice option for finding your answers before you get to them, or to just get them by graphing if that's what you're asked to do. Alright, if you have questions, reach out. Until next time, take care.